Okay, you can see the screen, right? Okay.
Yes, yes.
Yeah, so let me just begin with what are large language models. So basically, large language models are basically AI, artificial intelligence, that is designed to process and understand natural human-like language. So these large language models, or simply we call them LLMs, they are trained on huge amounts of data sets, huge data sets, and they allow generating human-like text. And when we when we engage in conversations with them, it tends to understand the context of the textual input and responds accordingly. And it is also able to translate languages, and it can summarize a text. If we give them a report to read, they can just summarize it in a few words and explain it in a simple way. And obviously, it can also answer questions. So basically, this is the really good buzzword right now, ChatGPT, which is a chatbot and under continuous development by OpenAI. It is one of the best examples of a large language model, and it is trained on a data set of conversational text. And as I just said, it responds really well to constructive input. Like when we give it really constructive pieces of text, it can process them really well and respond in a really good way, and provide some a really insightful output. And as we engage in conversations, it also becomes apparent that it is very context aware. So when we use these kinds of large language models, the most basic trend we see is to ask it in a technical way. But as through a lot of experimentation, it has been noted that and the trend right now is that most people are trying to understand it and approach it through a technical way. And a very important thing to note here is an artistic approach is also very important to when we communicate with such large language models. And so I'll just show you a small example of it. So basically, these are two very well-known personalities. On the left is a great poet named Rabindranath Tagore, and on the right is one of the great scientists of our time, which is Albert Einstein. And the thing is, on the left we have an artist, on the right we have a scientist. So how can we converse with the ChatGPT regarding this? Let's see this. So first I'm asking it a question. So respond to my queries as Rabindranath Tagore. What is life? So it says life is an endless mystery which can never be completely understood or explained. So that's an approach from a poet, an artist. So it's it's a perception towards life through an artistic approach, a poetic approach. But when we ask the same question as Albert Einstein, we have a different answer. We have an answer like life is riding a bicycle. To keep your balance, you must keep moving. So it's sort of a technical kind of answer. So what the approach I'm trying to point to is there needs to be a blend of these two approaches. One is the artistic approach and one is the scientific approach. So if I ask the next question like this, blend both the first two responses and answer the question based on them alone. So what does it answer? It answers that life is like riding a bicycle, an endless mystery that can never be completely understood or explained. To keep your balance and make sense of it all, you must keep moving. A blend of Albert Einstein and Rabindranath Tagore's views on life. So this is an amalgamation of both the approaches. So that's what I conclude in this next slide. That it is we can call it synthesis, which is a combination of science and art, where we approach problems using both the artistic and scientific methods. So when we ask this question to ChatGPT, what does it say? It says combining science and art can improve technological progress by bringing diverse perspectives and creative thinking to problem solving. So artists often have a unique ability to think outside the box and come up with new and innovative ideas, while scientists bring a deep understanding of the underlying principles and technology. By working together, they can combine their strengths to create new technologies and approaches that might not have been possible otherwise. So, like if we see if an artist tries to approach some problem, and if a scientist tries to approach a problem in separated ways, the solutions that we have wouldn't be as good as this scenario. So additionally, the combination of science and art can also lead to more meaningful and user-friendly technology that is better suited to the needs of people and society as a whole. So basically, how do we shape LLM behavior, large language model behavior? By combining the expertise of both the scientists and the artists. So on one hand, the scientists can provide the technical knowledge that is needed to train and optimize the large language models. And on the other hand, the artists can provide the creative insight that is needed to understand how the models can be used in real world applications. So together they are creating models that are not only highly accurate but also very easy to use, and they are very intuitive. So, and this is something that Meluk would like, really like, I think. So it reducing agile cycle times. So whenever we are working on any tasks, it can generate new ideas. It can solve complex problems, analyze large amounts of data, generate reports and summarize them. And it can also make predictions really quick. It can make organizations and companies more efficient and productive. And it's really good at automation, and repetitive and manual tasks become really easy to automate. And but how does it amplify human creativity in spite of all of this? Here is where synthesis becomes important here. So AI is providing all those kinds of amazing responses, but humans are the ones who are most responsible for providing the model with the data that it needs to learn, shaping its behavior through fine tuning and interpreting the responses in a way that is meaningful and useful for each and every task that is assigned to it. It is best achieved only through a combination of the artist and the scientist, combining the perceptions of both approaches. So basically, synthesis unlocks the full potential of artificial intelligence. This artistic approach provides a human perspective and understanding on how people interpret, use, and interact with the language, and which can inform the way in which the data is collected, pre-processed, and fine-tuned. On the other hand, as I just said, the scientific approach provides the technical knowledge and analytical skills which is required to train, optimize, and interpret the responses. So together, it creates a really highly accurate and easy to use model which can have a really great impact to society. So coming back to the ChatGPT scenario. So here you see I have underlined scaling over here. Yeah, so uh, this is the thing we are approaching. We see this a lot of the time, right? Whenever we are experiencing exceptionally high demand. Please hang on tight as we work on scaling our systems. So basically, this scaling is a centralized approach towards working with systems. So what they are trying to do, they are trying to improve the systems through a centralized manner. It is so. Could it be that that itself is a problem? So let's ask the question to ChatGPT. So when we ask this, compare centralized and decentralized scaling, what does it say? It says centralized scaling involves adding more resources such as servers or CPU power to a single central location to handle increased traffic or load. Decentralized scaling, on the other hand, involves distributing resources across multiple locations to handle the increased traffic or load. One advantage of centralized scaling is that it is relatively simple to implement and manage, but it can be prone to failure if the central location becomes overwhelmed or experiences technical issues. So this is what is happening with ChatGPT right now. Most of the time, you'll see that orange message hovering on the top. So it is basically that central location is becoming overwhelmed and experiencing those technical issues due to a lot of demand. So when it comes to decentralized scaling, you see that it can be more resilient to failure and as the load is distributed across multiple locations. However, it can be more complex to implement and manage, and that's what reminds me of NuNet's device management service. We can we can make it more intelligent to be able to handle such situations, and so which is under active development. Basically, large language models like ChatGPT can be even more powerful, like when we are using open source alternatives to it. So they can be trained on decentralized networks. We can allow the models to be trained on a much larger scale using the compute power of decentralized machines instead of just one centralized data center. And there is also a possibility to improve the models as they run across multiple machines while we resume interrupted uh, ML jobs that are actually training these large language models. So by rewarding the compute providers for running ML jobs, we could actually revolutionize the decentralization of artificial intelligence. And with this approach, we could create models that are not only more accurate and powerful, but also more accessible and affordable. Coming to a practical implementation of it, so there is an open source alternative to ChatGPT, which is Palm and RLHF. Palm is basically a pathways language model implemented through Google, and RLHF is a full form is reinforcement learning from human feedback. So using both of these approaches, uh, we are implementing an open source alternative of ChatGPT through Lucid Trains on GitHub. So this is the URL, the GitHub repository. So what we try to test on NuNet is the what the DMS is capable of doing through how it can start training of such a model on NuNet. So basically, this is a small excerpt of documentation of training an ML job that I recently experimented on in my lab. So it is basically we are starting a job uh, through the NuNet container. So this is a this PT is based on it's the name of a container image which is based on NuNet's Docker file. So it is designed to accept any kind of URL as a program, as a Python program, which can be which in this case is the Palm RLHF training file, and we can also add a dependency for it. So this is the format that we use in NuNet through the web app, which is under development. And using that framework, we can provide it any kind of file or dependency. So in this case, we are providing it a checkpointed version of the Palm RLHF training program, and as well as the Palm RLHF library, which can be installed via Python's pip package manager. So basically, I first tried running it on a 2060 machine, a 2060 GPU machine, and after it ran around 110 iterations, I interrupted it on purpose and just quit out of the program. And before doing that, I also saved a snapshot of the running job, and then I was able to resume it using this command on a different machine. So using this approach, we can go ahead and design our device management service and implement a decentralized way of training large language models. So that's all from my end. Thank you.
So, a question, Avi, what is the cost of running many of such jobs?
So basically, uh, if we run a job on a single machine, we have the ability now to continue that job on a second machine, a third machine, a fourth machine, and so on. So I think based on our onboarding use case, we can it is reliant on the onboarding procedure. So when an onboarded job is taking is performing training, if it is interrupted for some reason, it can switch over to a different machine, and the process can continue like a chain.
Another question. So, where does data come from initially, and how big is the initial training data?
This data is the data set that is being used in Palm is only around 39 MB. It is compressed.
Okay, and how big is the model in gigabytes?
It varies from data set to data set actually. In this case, it is using a NWIC 8, a dataset named NWIC 8, which is a compressed version of a huge Wikipedia dataset. That size is only around 40 MB, like 39 MB or something like that. Yeah, 40 MB. And there are other datasets as well. But the thing is, the program can be designed in any way, in such a way that you can download the dataset inside the container and start the ML job.
Okay, so following on that, can we actually run this scale training on NuNet? And if not, how far are we away from that place?
Actually, I think we are pretty close to that based on our DMS, how the DMS is capable of running jobs. And since we have our resuming capability, we can implement the commands through DMS, and so that different machines on the decentralized network can take over interrupted jobs and continue them. And we are also working on Joao is working on IPVS, and through that we could create a decentralized registry where we can push and pull images, and that would be very helpful for us to resume the jobs over the network. And basically,
Yes.
we compare this to a computational job. For example, if we are running a molecular dynamics simulation, so it can take days or even months for running huge jobs. So if we are able to continue, if we are able to resume these kind of jobs, it becomes very helpful. So each machine plays a part in running the job. So for example, if there is a job that needs to run for a week, so if a machine runs for a day, and a second machine runs for the next day, and the third takes the role for the third day. So in this way, all the machines play a role in running a massive job. So this is where we can compare the concept of nodes versus servers. Yeah, basically the costs would be based on individual machines. So that is the main inspiration behind NuNet is individual machines can play a significant role when they become part of a collective network. So that's the thing. Yeah, the computational cost would be basically one machine based on our phase one, which is the single GPU use case. So when one machine starts a job, the job can be designed to run millions of iterations. So each machine plays a role in running the job. So it could be a high-end machine or a mid-range machine. We would have three kinds of categories in the three kinds of machines in our use case. So each of them can play a role. So a low-end machine could be running the job for a small time, and perhaps it wouldn't be for very long, but it would still help in resuming an interrupted job in some way. So every machine has its own contribution. We are not using any like high-end data centers or anything like that. So we are using just home-based desktop machines. So this becomes a chain of running jobs on each machine.
Sorry, Avi, I lost my connection. Did you answer my question about splitting the inputs?
Yeah, so regarding the distributed training, we would splitting the data sets would be relevant because PyTorch is having its own distributed training modules. So that is another perspective of how the jobs could run on NuNet. So using those, so since the just as I discussed the ChatGPT alternative, it is a PyTorch based program. So if that program is redesigned in such a way that it makes use of the distributed modules of PyTorch, it can be run across multiple machines using the distributed modules.
Okay, thank you.
Yeah.
So I just wanted to ask, in terms of ChatGPT is pretty, I mean, not pretty big model, it's a huge model.
Yeah.
So, and you cannot really run it on one. So what do you mean when you say that we are pretty close? You cannot really run it on one machine, on one GPU. So the cost is more, the question is computational cost. How many GPUs we need to pull together in order to kind of reasonably run this sort of large scale language model? And yeah, that's the first. So this is in terms of computational cost. How much RAM? What is the size of the model? It's a billion parameters, which means terabytes, whatever. I don't even know what is the large. So what is the cost in this sense?
There are actually two approaches to it. One is the single GPU machine approach, and another is the distributed approach, where multiple machines are running the same program. So the thing that I discussed right now is the single GPU model. So one machine is running maybe we have a piece of code that is going to handle a huge data set, but the point is that we are able to resume it at one point where the first machine is no longer able to continue that job. So when the second machine is picking up that job from the first one, it is taking in all the optimization parameters and the model that is saved, the progress that is saved inside that model. So when this continues across multiple machines, that's when it becomes unique.
So I mean, so what I understood, what you tested now, you tested the like sequential approach, which is the first step to implement that, which means that you can, when one machine goes down, the job that was sent to that specific machine can be restarted on another machine without losing all the job.
Yes.
Snapshot. I mean, with that question, so for me, the question with that is, okay, so you do snapshot and you send this snapshot to somewhere, right?
Yes.
So how big is the snapshot then?
Big, actually, for the current test, I tested one job. It is around 10 GB in size.
So 10 gigabytes in size was the snapshot.
Yes.
So because from the NuNet perspective is, okay, we are running. What's important is how much memory do we use, which GPUs do we use, and what kind of bandwidth, let's say, how do you call it? I mean, how much megabytes and terabytes we are moving back and forth through machines, because if that's a huge amount, then it will be prohibited because machines will be hooked on the let's say internet, which may not be very fast. So that's kind of a question. Because if it's 10 GB of running a model, how many parameters do you have on this model?
This model is having Palm is having around 550 billion parameters actually. Palm.
Yeah, well, the model that you were running, you were testing. How many parameters did you train?
It is based on the Palm architecture, so that uses 550 billion parameters according to the documentation.
Yeah, right. I would really like to double check it. So that's 10 megabytes. I mean, it's too small. I mean, why? Or maybe it's not. But I mean, the size of the model should be in the same order of magnitude as the size of the ChatGPT model, which I believe is huge. I don't know the numbers actually. Otherwise, OpenAI wouldn't do what they do. They would make it smaller. So either we're training smaller model or we do not understand something. Because so
to handle the huge data sets, we can also try some compression methods to be able to handle the size of the data sets.
Yeah, but at the end of the day, if we want to run this kind of models, we will have to run different parts of the models on different machines in parallel. Otherwise, it won't work. Either we parallelize the model itself from the model training perspective, or as we talked or we do some sort of virtual GPU where the program itself will see all the machines and all GPUs across the NuNet network as one big machine with bunch of GPUs, which is like hardware virtualization sort of issue.
Basically, we are creating a massive virtual machine based on the onboarded machines. Based on that approach.
Yeah, so I still am trying to, because I mean, as we know, there is such a thing as the curse of decentralization, which is decentralization has a cost. So I'm trying to figure out, okay, so if we run this kind of models, there are certain pluses and kind of advantages to run large scale models on NuNet, but also there are computational costs just because it's decentralized. So I'm trying to figure out what is costs and benefits, or how do you say, pros and cons of running large models on NuNet. So what would be this decentralization cost? How much data will have to shuffle around?
We can say based on the NuNet use case, I think 3090 based machines like that are having GPUs such as 3090 or 3080 or 4070 that have come up in the market. But the thing is, when we say virtual GPU, I think it would be better to call it like a virtual processing unit because we also need to synchronize the CPU load and as well as the RAM also. So it is better to see it in that way.
We can call it virtual GPU cluster, let's say.
Yeah, we can call it that also.
And did you actually try to run this stuff on the mining rig?
The thing that regarding that I said in the presentation.
Fun?
I ran it on a 2060 machine, and I stopped the job, and then I was able to resume it on a different machine.
So my question is, can you run it on a machine with just more than one GPU hooked to it?
Yes, it can run because PyTorch can be programmed.
Okay, so that's straightforward.
Yeah, it can make use of multiple GPUs.
So the data that you were using, because let's say we want to let's take since you started with ChatGPT, let's take the ChatGPT as a kind of an example.
Yes.
How much data did they feed into it in order to train? Like the whole internet plus something else?
It is approximately, I think, based on recent info, it is around 640 GB, I think, actually. 640 GB.
640 gigabytes.
Gigabytes.
So how much data did you feed into the model that you tried?
This particular open source model is using a very highly compressed file, the data set. It is based on the entire Wikipedia information.
Okay, so entire Wikipedia, and how much is that?
40 MB. I'll just show you how it was compressed.
40 MB compressed. Okay. I mean, you can compress everything. So All right, and it resulted in 10 megabytes of model?
40 megabytes. I have it
Sorry,
in
40 megabytes.
right now. Yeah, 36.5 MB.
Okay, so and the way you, how many epochs did you run? Did you finish the training, or it was just yeah? I understand you tried out this snapshotting and
110 actually, 110 iterations, and it is designed to run up to 100,000.
200,000.
100,000.
100,000.
Author of the repository has set it as 100,000.
Okay, so how long did it take for you to run it on one machine, on one GPU? This 2029 and 2060, what was that?
I was able to run it like for 10 hours on a 2060 GPU, 10 to 12, 11 hours.
Okay, so so I think this is what these are the numbers that are interesting for us in order to figure out the use case for NuNet and what we need to do is all these times. Okay, so we ran this. Let's say we need to run 100,000 epochs in order to actually train the model with like normal accuracy that could be used. Then, by the way, we'll have to see the inference. How do we kind of run the inference?
Yeah,
but okay, so then in order for training, yes. Sorry.
I added one small code snippet to test the inference also. So currently, the main script that is there on the main repository doesn't have an inference model in there. So I just added one piece of code so that one can enter some text and see the output. But if we leave it out, it is also designed to provide some text, generate some text after every 500 iterations. So it will automatically show the quality of the text after every 500 iterations.
The point that I'm trying to sort of reach is so from the NuNet perspective, we are talking basically about two things. One is what NuNet as a platform has to implement in the platform features so that enable, let's say, large language models training and inference. From the NuNet perspective, actually, NuNet kind of doesn't care whether it's a language model or whatever it is.
Yes.
What it cares is about, okay, there is a container which is running some kind of stuff, which is just a lot of data, which is taking a lot of time. Therefore, it can stop, and we have to do snapshotting and exchanging this data and rerunning things. And we also need to parallelize a huge model, a huge kind of process to parallelize. And there are two ways as we talk. Either it's hardware virtualization on the distributed network, or some kind of model parallelization, which is already comes to the algorithm itself. So it's a kind of a general. Now,
this is basically yeah.
So another part that we're talking, and this is what you basically mostly seem to be, let's say, well, you come from there, is when you start with ChatGPT, is a kind of use case. Okay, but we are using those features in order to train language model and specific language model on this. And then this language model can have this many parameters. It can ingest this kind of data, whether it's Wikipedia, internet, or whatever, Library of Congress, I don't know what. So how do we do that? And then we calculate how much data needs to be pushed there. But based on the amount of data and amount of GPUs or amount of resources that we need to use for that. And eventually we're interested in this kind of size of models. Yeah, then we have to figure out what are the features that are needed on the platform. And the third aspect that you it seems that you started is, okay, but how useful that would be in general, for the community, for an AI community, and so that, and these are the, let's say, long, well, maybe it's long called, not that long term
if we are able to
effects.
If we are able to intelligently manage the storage, I think, and if we train it for maybe 3 or 4 weeks, I think the end result is going to be really something amazing.
Because so in order to kind of, what NuNet can do is enable community, like anybody who can connect to NuNet, and so we would enable people to run those models and to share the data between them, and then to use the trained models already to figure out whether they make sense, etc., and so on and so forth, and maybe retrain them to share how they train it, all kind of parameter configurations, etc., and so on and so forth, and to collaborate in order to get the model which makes sense. Let's say for maybe for the, we don't even need to say for the whole community. We can train sub models, and people can allow those models to be used by other people and to be, let's say, augmented and sort of made better or somehow retrained. And this is the potential from the basically this is where NuNet can make a difference on how AI is being developed right now. So this is basically our goal. So we kind of have three levels here. And while the last level is most kind of exciting, the result of all this and what we can get at it, but without the first level, which is basically how do we deal with hardware, we cannot reach it, the third one. And I'm sort of slightly sort of pushing down to this level of hardware. How do I exactly train this models, and how can we kind of draw the technical roadmap? How do we achieve that? It doesn't mean that we can sort of announce now that we can train ChatGPT out of nowhere. But let's say we can start saying this: if you trained, yes.
Yes, sir. The main objective was to see in this experiment was to see whether the current ML on GPU infrastructure that we have designed, when we use the PyTorch example, so we use the CIFAR 10 dataset for testing the ML job on the NuNet web app. So we just provided a program and we also provided a dependency. So my concern was, can we use that same approach for for Palm RL, the open source alternative to ChatGPT? So I see that there is no, we didn't have to give any extra effort to be able to run that model. We use the same approach to replicate that training.
And I think that's very cool. And what I'm saying that it's kind of as cool as it is, but it's the first step towards where we want to go. And I believe that we can now build also the containers in order to run these models, open source language models, apart from, I mean, besides what you already did, what we have for the GPU ML use case. Because as you said, we can run the same, we can use the same infrastructure that we have. We are sort of close to finishing. And then, yeah, I mean, if we can at least estimate, so how much work, and this is also related to our scaling proposal that you were working with, what kind of work we need to do in order to reach this sort of, let's call it virtual GPU clusters, to run the scale of models that ChatGPT is, well, kind of more or less this sort of magnitude. Maybe a little bit less for the beginning.
We need to also put some prioritization on the decentralized storage part, actually. So if we have a storage use case, we already have a computing use case, which is for NuNet. But if we also have a decentralized storage use case that synchronizes with the computing infrastructure, I think it would be a huge boost for us. So use case focused on decentralized storage, where people contribute their storage rather than the compute power.
So Joao is working on that. He can sort of confirm or disconfirm.
Yes, so I think we will get on this after the airdrop portal.
Yeah.
With, maybe with IPFS or not. It depends, because the main one of the main problems or not of IPFS is all data is public, so it may be a problem in some cases.
Well, from my perspective, it's not a problem, except that it's again computational cost. We'll have to encrypt data that is private.
Yes.
That is all.
Thanks, Joe.
Looks good. I'm looking forward to see what comes out of this. So thanks a lot, Ari.
Thanks.
Thanks, Avi.
Thanks, Joao.
Thanks, Avi.
Thanks, Jennifer.